Hello and welcome to the second video in the Newton's Law unit. In this video we are going to look at the different types of forces that we'll be investigating within this unit, except friction. And we will look at free body diagrams, how to draw them, and what they say. We'll also, during the process of this, talk about contact and field forces, which are two important types of forces that can act on objects. We're going to be drawing the diagrams for certain things, including the idea behind the safe and the feather, to prove once again that the rate that they fall at is the same for either one. So you can see from the terms here, these are the ones we'll cover. There are more that we'll cover. And we'll also try to get into the idea of what is a balanced versus unbalanced force, which we relate back to equilibrium. And we also talk about the net force in the x and y direction, which is an important concept that relates to the free body diagrams. First off, I'm going to take you through a number of forces and the labels that we will use when we draw a free body diagram. And a free body diagram, well, we'll define that in a moment. I want to make sure you have the forces that we will label it. Actually, it probably makes more sense to tell you what a free body diagram is, and then we'll talk about what the forces are for when we label them. So first off, please record this. I will also go through these ideas. A free body diagram is a diagram that shows all forces acting upon an object with their proper direction, label, and an estimation of their magnitude. In other words, when you draw the vector, you want to kind of show how strong the force is. If it's a very weak force, the arrow should be small. If it's a very strong force, it should be very large. So the steps to do this are very simple. You just draw a basic shape to represent the object and then make a vector for each force acting on the object, pointing in the direction the object would experience the force pointing. So if we were to say, why don't we draw a picture of you sitting on the chair that you are on, or standing if you happen to be standing like I happen to be standing. So first off, draw a basic shape to represent the object. That's as basic as they get, and that'll work. The next thing, we have to make a vector for each force acting on this object and point in the direction that I experience it if this were me being this object. The two forces I feel, I know I have a force of gravity because I am on Earth, and I'll draw the arrow a decent size, so I'm showing that it's a relatively large arrow. Now, in order to show that I'm not falling, because right now if I said this right now, this is what's known as unbalanced. And because it's unbalanced, that means I am accelerating. Ooh, that's ugly. Because I have a net force. You can tell I have a net force because I have only one force acting on me, so overall I have one force that is winning, because there is only one force. It's unbalanced. I would be accelerating right now. I'd be falling. So clearly I'm not falling. I must have something resisting my attempted motion, and that is the normal force, which you can write as this. I would want to show that they're equal opposite, which is to say I'm not actually falling down or jumping upwards right now. They are equal opposite. You can't necessarily tell by the length of my arrows. Actually, I think my normal force arrow is slightly larger than the force of gravity, which isn't good because they should be equal opposite. In this case, this is balanced. No acceleration in this case. And we will be going into this more as we go. So this is just a basic one. Well, I knew to label this, and now I need to provide you the forces so you can do this as well just as easily. So first off, we need to know the key forces on their labels. Weight is also referred to as the force of gravity. We abbreviate that F with a little g. And by the way, it can be easily calculated. Fg is calculated as mass times the acceleration of gravity. And the acceleration of gravity changes depending upon the planet you are on, so your weight changes. But keep in mind, mass does not change. Based on location. And that's a very important thing, because my weight can change if I go to a city that's further away from the center of the planet, in other words, higher up above sea level, I weigh slightly less because I'm in a different location. My mass didn't change because if I go from here to Denver, Colorado, I'm not gaining or losing mass just to do this, but I'm definitely changing my location, and therefore my force of gravity has changed. So the label for this, by the way, we labeled it Fg on a diagram. Next one, normal force is the resistance of a solid object to things passing through it or trying to break it. And it is always perpendicular to the surface, and it is always opposite direction to the force acting on the surface. In other words, let's say we have a person who's leaning against a wall. There's a wall here, and we'll say that they're leaning against it. And this is going to turn out to be a force applied. They're leaning against the wall with a force applied, and let's say it's I already used that number. So it's 300 newtons going inwards. The normal force would have to be this wall. This wall doesn't want me to pass through it. So rather than it breaking and letting me fall through, it supplies 300 newtons in return in order to balance me out. And we label this, there are two ways to label this one. That would work, and a scripted N would work as well. Either one is acceptable. By the way, I would want to say that those are balanced forces. They are equal and opposite, which means that this object is not accelerating, is not changing its speed, which makes sense because if I was leaning against the wall, I have a velocity of 0. So that's good. I don't want to say that I'm accelerating. Otherwise, I have to say the floor or the wall broke or I'm getting pushed off the wall. So normal force. And by the way, just as a fun little example, if you put a block on an incline, which I believe we covered in some of the hours already, this is the surface here, right? Which means the normal force in this case must be perpendicular to the surface. It must be pointing this way. It wouldn't be pointing downwards because downwards is the direction that the gravity of this object is pushing. It must be pointed up and out. Next force we're going to look at is tension. And this is the force in a cable, a wire, a cord, a chain, anything that can be called basically any of these types of shapes that allows it to hold up whatever is attached to it. So, for example, let's draw a free body diagram for a rock held up by a string. So in other words, somebody tied a string to a rock. First off, we start by drawing a basic shape for the object. That works. A circle can represent just about anything. Now we need to draw the forces acting on this object. If I were to draw the rock attached to a string, I could do something like that. It's a pretty ugly rock, but it'll work. So the force of gravity is obviously pointing downwards because it always points downwards. Now tension must point in the direction that the cord wants to pull this thing. In other words, which way is the cord having to pull this thing so it doesn't break the cord and fall? So tension must be pointing upwards, opposite of gravity. Now if we assume that that thing is not moving, as in it's just sitting there and I'm holding the string in a rock and it's not going up or down and I'm not falling, then these two must be equal and opposite. They must be balanced, which means there is no acceleration. That's a key idea. Again, balanced forces mean no acceleration. Does that mean it's not moving? Not necessarily. No acceleration just means you're not changing your speed. What if you were going at a constant velocity? We'll cover that shortly. So for tension, we've now seen how to show that one properly. Next one, force applied. This seems confusing at first, but basically it's any time an object is applying a force to something. Like if I was the object, I can apply forces to things because I have muscles and such. I can use my muscles to apply a force to something. My car can apply a force to the road through the tires because all I have to do is hit the gas pedal and they rotate more and I'm going. So a force applied is an object supplying motion to something else. So let's do a multitude example here. Let's assume we have a person pushing a book to the left on a frictionless table. So we're going to first off draw our object, and a book would be very easy to represent as a rectangle. And this object is on a table. Okay, that's going to mean that we have a couple other forces to draw. First off, force of gravity. Why not? There we go. Next thing, it's on a table, which is a solid object, and the object doesn't want the book to just fall through it. So there must be a normal force of that table resisting the book falling through it. Now before we move on, the book isn't falling through the table and isn't going off of the table. These two forces have to be equal and opposite in order to show that this book is not going through the table or jumping off the table. Now, the person is pushing a book to the left. So the book feels something pushing it to the left. We abbreviate that FA. The label for this, by the way, is FA. For the previous, I apologize. I don't think I actually gave you the label for what is tension without basically writing it there. The label for tension is a big T. Alrighty, so for this one, a couple key things to make as a point. We have two balanced forces. So our vertical forces are balanced. So there's no acceleration vertically. Horizontal or not. So horizontal are unbalanced. Now if that's true, we must have a horizontal acceleration. So we have a horizontal acceleration. Now if that's the case, you can calculate this. if there's ever a net force, oops, sorry, F net equals ma. And that's how we find the acceleration. So we know mass, we know acceleration, we're looking for this one, we'd say. Well, what is our net force? You can always separate x and y directions, keep that in mind. Our net force means what force is winning overall. What force is unbalanced? We have a force applied. So in this case, our force applied is equal to ma. And if we knew that force and we knew the mass, we could easily find the acceleration. We'll do some examples in the future to show how that works. The force on a spring is interesting. And there's a law that defines how it works. We abbreviate this as F with a little s to say force of a spring. So the force of a spring, basically any object that's attached to a spring feels a force from the spring. It's defined by what's called Hooke's law. Hooke's law is this. Force of a spring is equal to negative k times x, where k is the spring constant, when it basically says how strong is the spring. And a way to kind of think about that is when you click your pen, if you have one of those clicking pens, they have a spring in them that's very weak. The spring constant on one of those springs is very low. Now a car or a bike that has shocks, a spring built into it, those springs are rather strong. They have a very large value of k. So the shocks in your car when you're driving it, these are large springs, and they have a huge constant k for their spring value, for their spring constant, sorry. X is basically the same thing as saying delta x. We could also have written this as such. It is displacement. And basically a spring wants to be in a certain length. And if you've ever seen one before, they basically, if you aren't touching it, they're a certain length. And then you can kind of squish them or you can pull them apart and they separate away from where they were originally. Now, that's a displacement. However far you pull it away from where it wants to be at rest, that's the displacement. And the more you pull it away from rest, the stronger the force gets because the more it wants to return back to rest. Key idea here, there's a negative sign in the equation, and that negative sign means only one thing. It means that the force acts in the opposite direction of the displacement. That's what the negative sign means. So if I was to say, and by the way, when we draw springs, we actually draw them as like a little pigtail thing. If this was the rest position of this spring, and I was to squish it inwards until it was smaller, I'd be this far in. This would be like my delta x. And I went in the negative direction, which means the force is pointing in the positive direction, right? So my delta x is going to the left, whereas my force is going to the right. Sorry, these arrows are, for some reason, there's a bad spot on this board here. There we are. Force of a spring. Next one, air resistance. The only type of friction I want to tell you about quite yet, for right now. We'll talk about friction as a solid object later, or between solid objects later. A type of friction of a fluid or fluid-like medium. So when an object is moving through a fluid or a fluid-like medium, it experiences something similar to air resistance. So you can call it, I call it air resistance because we're basically going to look at it in the air. That's not very proper. Really better just to call it resistance or the resistivity of something. Well, it's abbreviated large R. That is the label. Is equal to negative B times V. And the constant B is basically related to the density of the substance. So obviously falling through air or falling through, say, water, the density of air compared to water, well, that'll show with this factor B. In other words, if it's something falling through air, B is low. Density is low, so B is going to be lower. Falling through something thicker like water, then B is going to be higher, and there's going to be more resistance. So it also relates to the surface area of the object. I should say surface area, sorry. And that has a lot to do with, say, skydiving. That if a skydiver were to tuck their arms and legs in and fall, they'd fall a lot faster. They'd experience less air resistance than if they were to spread their arms and legs out and fall kind of like a frog leaping. That has more surface area, which means they get a higher B value, which gives them greater resistance. And lastly, the velocity is V, and that's interesting because the resistance is increased with increasing velocity. So the faster something is going, the stronger the resistance to passing through it. That should be fairly interesting. We'll talk more about why that comes into play, and it does relate to how fast you're going compared to the medium itself. The negative sign is here again, and it simply means that the resistance R is always opposite in direction to the velocity. That's really all it means. So if I was to draw a picture of a car driving down the road, that is our next free body diagram. So our example is going to be a car driving on the road at a constant velocity. That's going to be important right there. Because what does constant velocity mean? There can be no acceleration. We're going to ignore friction, but we're not going to ignore air resistance. So here's our car. That's just a fine way to represent a car is a brick. And basically, look, well, it's a free body diagram. Anything can be approximated to a very basic shape. What are the forces acting on this car? Well, first off, gravity, and I'll draw a fairly large arrow because it's probably a big object. It is driving on a road, and a road is definitely a solid surface, so we'll do a normal force arrow for that. Next thought to have, well, the force of gravity and the normal force should probably be equal because it's not falling through the road and it's not getting thrown off of the road. These are balanced forces. There's no vertical acceleration. Now, I didn't tell you which way it's driving, so I'm going to decide by drawing a separate arrow with a V on it to say that's the direction of the velocity. They are driving horizontally to the right. I'm going to assume that if they are driving to the right, then air resistance has to be opposite of that. And notice I've drawn, oops, let me make that a little more clear. I've drawn the air resistance arrow smaller than the force of gravity and the normal force arrow because I'm imagining that the air resistance force is probably less than the weight of the car. That's that idea of the magnitude. I could be wrong, you never know, but without knowing, I would guess the air resistance is probably less than the normal force and the force of gravity. But we're supposed to say a constant velocity, so that makes us think about this and say there's a problem because it's clearly unbalanced in the horizontal direction. We have a R for our air resistance and nothing on the opposite side. Something must be happening. If you've ever been driving down the road, in order to continue going in a straight line, in order to continue driving forward, you do still have to give the car gas. As soon as you let off the gas, you coast to a stop. And there's a reason. There's lots of resistance against your car's motion, against its inertia, you could say. I'm going to assume that we can approximate the effort of the engine to move the car as a force applied. And because it's a constant velocity, force applied has to be equal to the air resistance, otherwise there would be unbalanced forces, and therefore there would be an acceleration. So we have balanced forces in the x direction and balanced forces in the y direction. You could call this equilibrium. There is always equilibrium when there are balanced forces. This is an equilibrium horizontally and vertically. Let's try something. Let's try drawing that car coasting to a stop. This one's normally tough. Car. Has to be a force of gravity, and I assume it's a big object, so I'll make it larger. Has to be a normal force because it's not falling through the ground or getting thrown off the ground, and they're definitely equal and opposite. I'm going to draw and indicate that it was going to the right. And keep in mind that velocity arrow cannot be on my free body diagram because it's not a force arrow. Velocity is not force, so it can't be on my diagram. It can't be a part of this object. Now, it's driving to the right, which means air resistance has to work exactly opposite of velocity. So that gives me an R pointing to the left since I decided it was driving to the right. And right now, consider what this says. Equilibrium in the vertical direction. In other words, there is no acceleration vertically. Right now it says that there's just a horizontal force. So it says that there is a net horizontal acceleration. So we can say F net, and you can even say X next to that to say just horizontally, is equal to mass times horizontal acceleration. Well, we now know the net force is R. That's the overall force working against it. And that must be equal to m times acceleration in the x direction. So there we go. We have an unbalanced force in the x direction, which is allowing it to accelerate. And in this case, think about it. If the force is working in this direction, so is the acceleration. And our acceleration is opposite to our velocity, which means this object is clearly slowing down. Those are the basics. We'll start doing calculations with this next, but this is what you need to know to get to that point. Thank you for your time, and please let me know if you have any questions on this.